Hello, friends, and welcome back. This is the beginning of what would have been the lecture for Thursday, April 30th, 2020. Sadly, we're all still in quarantine. I hope you and your family and your loved ones are safe and healthy. And let me know if there's anything that I can do to make your end of semester experience a little bit easier. We're all going through this together. Just to remind you, there's a CAPA due at the end of this week. And there's another CAPA that will be posted sometime soon if it hasn't been already, and will be due middle of next week on Wednesday, the last official day of classes. We'll have one more set of lecture videos that get posted for next week for Tuesday's class, and then I'll have more information probably at that time about details about the final. But the final will be the following week, probably Monday through Thursday. You'll have the chance to take it. And it will work very similar to the other ones, except it will be cumulative over the whole year, and it will be longer. But other than that, it will work very similar to exams 2 and 3. So we are wrapping things up. We're thinking about the biggest questions that can possibly be asked. How old is the universe? How big is the universe? What is the shape of the universe? Where are we in the universe? And so let's get right back to it. There's lots of fun stuff to do. Here we go. Today's review question. Where is the center of the universe? Is it the Milky Way galaxy? Is it somewhere near the edge of our visible universe? Is it so far away that it's outside of our visible universe? Or is there no center at all? Pause it if you like. I'll tell you the answer now, though. The answer is that there is no center. If you don't remember that, I think it was video 3 in the last class where we talked about why that is the case. We did a cool little demo. In fact, one of my favorite demos of the whole year. The whole galaxy's expanded by a factor of 10% trick. So the fact is, we think there is no center. We'll talk much more about the shape of the universe and what we think it is in today's class. That's one of the things that we're going to be talking about today. So here we go. Chapter 27, active galaxies, quasars, and supermassive black holes. It's a very cool chapter, which sadly we don't have much time to talk about. So if you're interested in active galaxies, quasars, and supermassive black holes, and let's face it, who isn't? You should go ahead and read chapter 27. We're going to take a snippet from chapter 27, which is to continue our discussion about dark matter. You might remember that, rewind when we were talking about the Milky Way, that we measured the Milky Way's mass. We put it on a scale. How did we do that? We took the sun and figured out how far it was away from the center and figured out how fast it was orbiting the center of the galaxy, what speed it was, and there was a formula. We could just plug those two numbers in and it gave us the mass of the galaxy that was inside of our orbit. And we could do that for all of the orbits, all of the velocities and all of the distances, and get not only the mass of the entire galaxy or within our orbit, but inside of any orbit, and get the mass distribution of the Milky Way galaxy. And what we found that the mass within the sun's orbit was about 10 to the 11 solar masses. And if you go out to the edge, you've got about another factor of 10, about 10 to the 12 solar masses. A trillion, 100 billion inside the mass of the sun, another factor of 10, 10 to the 12 or a trillion solar masses inside in the galaxy as a whole. And you might remember that this is way more than the actual matter that we see, the normal matter, the visible matter, the luminous matter in the galaxy, by a factor of 10, almost. And in fact, if you were to, you would expect, in fact, not only that, is there more mass within the galaxy, but it extends much further than we see the galaxy actually extending to. So here is the visible edge of the galaxy. We would expect, even if there were no dark matter, even if we could explain all this luminous matter, which we can't, we would expect once we get outside the actual matter of the galaxy that it would fall off in a Keplerian way, because this is what this is what velocities do when you're outside all of the mass, just like the solar system. Instead, not only do they not go down, they actually go up. So this is telling us both that there's lots of dark matter within the galaxy in the center. There's also a halo that extends well beyond the visible limit of the galaxy, where there's just a lot of stuff out there that we can't see. And we call this stuff dark matter. In fact, if you were to look at a true diagram of what the galaxy actually looks like, it's probably more like this. Here is the disk of the galaxy. Here is the bulge of the galaxy. Here's those halo and the globular clusters that we're talking about before. This is all the luminous matter here, most of it concentrated in the disk. The dark matter halo of the galaxy extends much beyond the actual luminous matter of the galaxy. In fact, if you're going to say, what is the galaxy? It's actually this thing. 90%, almost 85 to 90% of the total mass of the galaxy is in this thing and not in the spiral arms or the disk or the bulge or the globular clusters. Almost all of the galaxy, the matter of the galaxy, the mass of the galaxy is in this dark matter halo. So that's the Milky Way. We've done lots of calculations on the Milky Way. We hopefully have a good handle on that. Is the Milky Way unusual? Are other galaxies similar to the Milky Way? Well, we can go out and measure these things. We can measure the rotation curves of other galaxies, measure how fast stars are orbiting those galaxies as a function of how far they are from the center. And when we do that, we get something that looks like this for other galaxies. Here are 4 of them. And look, they all look about the same. And they all look pretty similar to the Milky Way. The Milky Way has this steep rise at the center, and then it goes about flat at about 220 kilometers per second. The Milky Way isn't on here, but if it were, it would fit right in with these. Look, these galaxies behave in exactly the same way as the Milky Way. In fact, all spiral galaxies seem to obey this relatively constant flat rotation curve law. And so it seems that, again, this is even further out than we went before. We only went out to about less than 100 for the Milky Way. These things extend, in some cases, much further than that. So again, the visible light of their galaxies is probably contained to this region, and this dark matter halo extends way further beyond the edges of their galaxies, just like the Milky Way does. So it seems that dark matter is not just a local problem, it's a thing that happens everywhere in the universe. All of these galaxies seem to show this. Okay, so, well, that's weird, right? It's uncomfortable. We don't really want to be in a position where it's the year 2020 and we think we know what's going on and we're pretty highly thought of ourselves and our technological advances, and we don't know what 90% of the universe is made of. But this seems to be the way it is. It would be better if there was some other explanation for this. So maybe we got this rotation thing wrong. Maybe the law that the equation that we use to calculate these masses is just wrong in some way. Maybe there's some other way we can measure the mass, and that will give us a better value that won't have all this problem where 90% of it's missing. Well, let's look for some other ways. Here's one. This is cool. Remember, we said that light is affected by mass. In other words, light bends around mass the same way that mass bends around mass, and it can enter orbit if you're close enough to, say, a black hole. Even if you're not near a black hole, here is an example of a cluster of galaxies, a huge amount of mass. Each one of these galaxies is way bigger than the Milky Way. This is probably a Milky Way-sized galaxy. These guys are probably orders of magnitude more massive than the Milky Way. And there's a lot of them all in one region of the sky. Well, if you have a galaxy that's more distant than that, the light, as it passes by this very massive object, will get bent a little bit. And so you'll see this galaxy isn't where it doesn't look like it's where it actually is, because its light has been bent around this foreground galaxy cluster and distorted it. We call this gravitational lensing. And in fact, it's probable that this galaxy and this galaxy are exactly the same ones. You can almost see the shape. It's been distorted a little bit, but you often can get multiple images of the same galaxies. In fact, the true position of the galaxy is probably right there, right in the middle. You can almost see it in there in the middle. This is a background galaxy, and you're seeing 3 images of it for exactly this reason, right? You've got the real galaxy whose light passes straight through, and then you've got some light from this galaxy that would have gone in this direction, and some light of this galaxy that would have gone in this direction that get bent, right? Gets bent around this galaxy cluster, and so we see another image of this galaxy. When we're looking back on the Earth, it looks like it's here, and it looks like it's here, but these are actually the same galaxy, and we can do redshifts, and they have the same redshift, and they have all the same properties. We can actually measure it. It is the same galaxy. We're just seeing it 3 different times. And that's cool, right? Here are some other examples of gravitational redshifts. Look at these things. It's sort of like taking, I don't know if you have a glass. Do this tonight. Here's your homework. Take a glass from your kitchen that you would drink out of. Go outside and look at a street light, or look at a bunch of street lights. They're going to look like this. You're going to get these weird arcs and trails and things. And that's due to simply light being bent in this case, around galaxies in your cup through the glass surfaces to get to your eye. And so that's cool, and it's interesting, and it's really fun to look at. Look at all these streaks, and they get distorted and turned into lines and things. But even cooler is that you can use this based on the geometry of where this galaxy is and where the background galaxy is and how far that's bent to measure the mass inside the galaxy cluster. Not just the galaxy, but the cluster as a whole. And that's a totally independent way to do it. You're not talking about radial velocities. You're talking about gravitational redshifts and distortions as it moves around. Totally independent way to measure the mass of something. And yet we get almost exactly the same number. So it seems to be a number that's independent of how we measure it, which leads credence to it. Maybe this is a real thing. I want to step back. So I don't think it's that we're missing the amount of, well, but maybe it is. So let's think about 2 possibilities for what our options are for this dark matter stuff, because it's uncomfortable. We don't want to have huge amounts of missing mass in the universe. So our options are this. Dark matter really does exist, and we're observing the effects of its gravitational attraction. Or it's certainly possible, and this is the way science works, something is just wrong with our understanding of gravity, causing us to mistakenly infer the existence of dark matter now, not only through the radial velocities, but also with the gravitational lensing. Believe me, number 2 is a much better, more comfortable possibility. But like Sherlock Holmes says, if you've eliminated every other possibility, then whatever remains, however unlikely, must be the case. People have looked very hard for this number 2. People have tried very hard to develop theories of gravity that can explain all the observations with the Milky Way, with other galaxy clusters, and explain everything else, and they haven't been able to do it. Very smart people. Imagine if you're the one who does this, can explain how gravity works and explain dark matter in some elegant theory. You're world famous. You're at Einstein. You're going to win a Nobel Prize. This is the biggest thing that could possibly be done now, with some exceptions. But it's very big. People have tried very hard to do this, and they just can't. It doesn't seem to be possible. And so let's think about this. So our dark matter then maybe really exists. Maybe there is this thing out there. We don't know what it is, but we can investigate it. We can try to figure out what it is. So in the next video, we'll be thinking about ways that we can, things that this dark matter could be, and ways that we can observationally look for this particular kind of dark matter. Stay tuned.